Hello and welcome to this course, where I shall be discussing authentication, authorization and accounting, and the variety of these three mechanisms that are available to you within AWS. Having an understanding of the different security controls from an authentication and authorization perspective can help you design the correct level of security for your infrastructure. Once an identity has been authenticated and is authorized to perform specific functions, then it's important that this access can be tracked with regards to usage and resource consumption so that it can be audited, accounted and billed for. Before we start, I'd like to introduce myself. My name is Stuart Scott. I am one of the trainers here at Cloud Academy and I specialise in AWS, Amazon Web Services. Feel free to connect with me with any questions using the details shown on screen. Alternatively, you can always get in touch with us here at Cloud Academy using the community forum where one of our cloud experts will reply to your question. This course has been curated for an audience who have an interest in cloud security and may be in a position of a cloud solutions architect or cloud security specialist or similar. This course will cover a range of topics including authentication, authorization and access control. Here I shall be looking at the differences between these three terms that often get confused. Then we'll look at authentication mechanisms, and in this lecture I will examine the different authentication mechanisms available within AWS. Following this, we'll take a look at authorization in AWS. There are a variety of methods to authorize an identity in AWS, so in this section I'll cover some of those most common. Finally, we'll take a look at AWS Accounting. When looking at accounting, I will define what this is and dive into AWS billing and cost management, along with an overview of the AWS CloudTrail service. As a student of this course, the content will provide you with the following: clarification over the differences between authentication, authorization and access control, an understanding of the different authentication mechanisms used by AWS, an understanding of the different methods of granting authorized access to different AWS resources, how a combination of authentication and authorization mechanisms can be used to create solid security policies, an overview of how AWS billing can be used to help spot security breaches, and then finally, how to track a user within AWS and monitor their actions through audited API call requests. The prerequisites for this course require a basic understanding of Identity and Access Management (IAM), EC2, S3, some networking fundamentals, and the Virtual Private Cloud Service. Feedback on our courses here at Cloud Academy are valuable to both us as trainers and any students looking to take the same course in the future. If you have any feedback, positive or negative, it would be greatly appreciated if you could use the comment section found on the landing page of this course. That brings us to the end of this lecture. Next, I shall explain the differences between authorization, access control, and authentication. Welcome to this lecture on authentication, authorization, and access control. When talking about security, I find that there is always a lot of confusion around the definition and meaning of the words authentication, authorization, and access control. Many people believe they all mean the same thing, with no clear distinction between them. This is, however, untrue, and as a result, people often use the wrong term to describe their security mechanisms. In this lecture, I want to cover each of these to help you understand the differences. It's important to know these differences in order to control access to your cloud resources effectively, and with the appropriate level of security. Let's start by looking at authentication. The authentication process is comprised of two parts of information. The first part of this process is to define who you are, effectively presenting your identity. An example of this would be your login username to your AWS account or environment. This identification is a unique value within the system that you are trying to authenticate to, and in this example, AWS would not allow two identical user accounts to be created within the same single AWS account. The second part of the authentication process is to verify that you are who you say you are in the first step. This is achieved by providing additional information, which should be kept private and secret for security purposes. However, this private information does not have to be a unique value within the system. So in the example I just gave, whereby you provide your identity in the form of a username to your AWS account, which will be a unique value, the next step would be to verify that identity by providing a password. Putting AWS in the cloud to one side for a moment, usernames and passwords are not the only forms of authentication from an identity and verification process. In our everyday lives, we are presented with multiple forms of authentication methods. For example, credit and debit cards and PIN numbers. So when we use these to pay for something, we authenticate to our banks. In this process, we firstly identify ourselves by providing the credit card details with our personal information on, and then verify this identification by entering a private secret PIN number. This combination then allows us to authenticate to our banks. Authentication is not just for verifying human access to systems. Authentication takes place by systems that require access to other systems. For example, one AWS service requiring access to another to perform a function. In this instance, the same authentication principles and processes followed. Identity first, and then verification of that identity. Now that we have a clear definition of authentication, let's take a look at authorization and see how authentication and authorization differ from each other. Authorization only takes place once an identity has been authenticated, so there is a clear order as to which these two operate. Authentication takes place before the correct level of authorization can be attained. Authorization is the process in which a system you have authenticated to establishes what you can access and at what level. So here we are really looking at your access privileges and permissions. Staying with our AWS example, we have authenticated ourselves by providing the correct identity and password. Now AWS security features, and in this case AWS IAM, Identity and Access Management Service, defines the level of authorized access assigned to that identity within the AWS environment. Each identity can have a different level of authorization properties associated to it. It's these properties that determine what that identity can then access. Let's say we have 4 identities within our AWS account: Stuart, Andy, Ben and Eric. Once authenticated, AWS would then determine their authorization levels. This table shows the high-level authorization information. From this, we can see that Stuart is authorized to have full access to the complete AWS S3 service. Andy is authorized to only launch instances from within AWS EC2. Ben is authorized to only create volumes within AWS EBS. And Eric is authorized to both create and delete users within IAM. So there is a clear distinction between authentication and authorization. Authentication identifies and verifies who you are. Authorization determines what an identity can access within a system once it has authenticated to it. Now, how does access control fit into all this? Again, access control is defined as something different to authentication and authorization. Access control can be classed as a mechanism of accessing a secured resource. Let's put some examples and context around this to make it a little clearer. When a user logs on with a username and password, as per our previous example, this mechanism of access control, in its most simple form, can be classed as a username-password method. If we were then to include the use of a multi-factor authentication device, MFA, then the access mechanism would be associated closer to MFA, as it's a greater level of authentication to that of just the username and password. So access control is more about the process of how access is granted to a resource. Let's go over this again with some other access control mechanisms within the AWS environment that you should be aware of. It's important to note that it's not always related to a human, and access control systems can be exchanged by AWS services themselves. So some other methods of access control within AWS can be IAM roles, where roles are used to grant permissions to perform specific functions. This can be classed as role-based access control. Federation. This is where access is granted to users that do not have identities within AWS itself and are supplied temporary credentials to gain access. For example, a user account within a corporate on-site Microsoft Active Directory can be federated to access AWS resources. Network Access Control Lists, or NACLs. This method is performed at the network layer, restricting data dependent on specific network parameters such as IP address, protocols and ports. For example, only allowing SSH access to a particular subnet from a specific network range. Security groups. Similar to NACLs, they perform the same function but at the instance level. So again, access control based on IP address and port information. So as you can see, it's not always related to human activity where usernames and passwords are used. Access control is very closely related to both authentication and authorization, as the access control mechanism typically is used for both authentication and authorization to gain access to a resource. So, to reiterate, I feel it's important to really understand the difference between the three terms we have just covered. Authentication, the process of defining an identity and the verification of that identity. An example would be a username and password. Authorization determines what an identity can access within a system once it's been authenticated to it. An example of this would be an identity's permissions to access specific AWS services. Access control, the method and process of how access is granted to a secure resource. An example, multi-factor authentication that we just discussed. I hope you now have a clearer understanding of the differences between each of these terms and that you see the clear difference between them. AWS has services and features for the three mechanisms we have just learned, and so it's important we use these in the correct context and not to confuse ourselves and others between their meaning. This brings us to the end of this lecture. Coming up next, we'll look deeper at authentication to discuss the various methods of authentication available in AWS. Hello and welcome to this lecture on AWS Authentication Mechanisms. Authentication is the first component of authentication, authorization and accounting. It's the first process that takes place. Without authentication, authorization and accounting simply can't happen. In the previous lecture, we briefly covered authentication methods, but here I will drill down into a wider variety and at a deeper level so you can understand how each of them work. Starting with AWS Identity and Access Management Accounts. IAM is used to securely manage users who require access to your AWS environment. During the creation of identities of users, there are components and features that you can use that affect how these users authenticate. The most basic is that of a simple username and password. These usernames need to be unique as they identify you as an individual and therefore can't be duplicated. The password, however, can be duplicated between different users. IAM allows you to specify your own password policy that gives you complete control on how secure you want the passwords in your environment to be. Custom changes can be enforced within the password policy, such as requiring uppercase, lowercase, numeric, non-alphanumeric characters. Additional attributes can also be set to ensure users' passwords are changed after a set period of time and restrict the use of previous passwords. A minimum password length can also be determined. I would always suggest enforcing a tight security policy and adopting as many of these parameters as possible. With this authentication mechanism, all that is required to determine the identity is the username, which is then verified by the correct password that adheres to any set password policy. IAM will then verify if the authentication is successful. If the credentials do not match with those held by IAM, then access will be refused and you'll be asked to re-enter the correct information. If the authentication is successful, then the user will be allowed into your AWS Environment Management Console with the authorization to access any resources as specified by the permissions given by IAM associated to that user. Usernames and passwords aren't generally considered hugely secure, as the users are allowed to set their own passwords, which can often be guessed, and laziness can lead to standard passwords being entered, such as password in all lowercase, 123456, QWERTY, and let me in. Although AWS allows you to enforce password policies, combinations of the above still make their way in, such as password 123 exclamation mark, which is both uppercase and lowercase letters along with numerics and non-alphanumeric characters. So with this in mind, tighter security can be achieved with the use of additional authentication methods, which requires additional credentials. IAM allows for multi-factor authentication, MFA. This means that any user configured with MFA must use an additional level of authentication as well as a password to be authenticated, giving an additional layer of security. This additional authentication utilizes a random 6-digit number that is generated by an MFA device that is only available for a very short time period before the number changes again. There is no additional charge for this level of authentication. However, you will need your own MFA device, which can be a physical token or a virtual device. AWS provides a summary of all supported devices here. Personally, I use Google Authenticator on my phone because it's simple and easy to set up and configure. Before a user can authenticate with MFA, it must be configured and associated to the user, As we know, as a part of the authentication process, we need to ensure that the verification part confirms the identity of the user. This configuration and association is done from within IAM, and I will now show you how quick and easy this is to do via a quick demonstration. Okay, so I've already logged into my AWS account, and the first thing I need to do is go to IAM, which is under Security, Identity and Compliance. So we need to go into IAM to select the user that we want to give multi-factor authentication to. So if we go over to the users, and I have a user here, CA user 1, Cloud Academy user 1. So if we select that user, if I go across to security credentials, we can see down here that the assigned MFA device is no. So we want to give this user an associated MFA. So if we click on the edit button there. Now I'm going to be using Google Authenticator on my phone as the MFA device. So that's a virtual MFA. So select that and click on next step. Now this is a quick splash screen just saying that if you do have a virtual MFA, you need to install a compatible application on either your phone or PC, etc., which I've already done. Like I said, I'll be using Google Authenticator. So we can just skip past that step. Now, as a part of the setup of the MFA with this associated user, we can scan that QR code using Google Authenticator, and that will give us two activation codes. The first one, which will go in this box here, and then after a few seconds, it will give us a second code that we enter here. So this is just to synchronize. So if I go ahead and do that, so the first number is 745559. Then in just a few seconds, that will present me a second number as a part of the synchronization process, and that's 443393. And then we simply click on Activate Virtual MFA. So it's given us a message saying that the MFA device was successfully associated. So if we finish that and try to log in as this user. So the username was CA user 1. I'll put in the first authentication method, which is the username and password. And you'll see here that the MFA users need to enter their code on the next screen. So by clicking sign in, it should present us with another authentication screen. And here we are. So here we need to enter our MFA code. So if I go back into my Google Authenticator and take a look at the number issued by the user, 061695, and click on submit. And there we go. We're authenticated into the AWS Management Console, where I can then access any resources that I have permissions to. Sometimes logging into the AWS Management Console isn't required by an individual or identity. Instead, access is required from a programmatic perspective for a user or service who may be using the AWS Command Line Interface, the CLI, AWS APIs, tools for Windows PowerShell, or software development kits. When using any of these methods to access AWS resources, access is not granted to the AWS Management Console. Instead, you are accessing the resources programmatically, and so you must authenticate differently. This is typical of any application that calls upon functions of other services. When an identity is making programmatic calls to your AWS resources, that identity is not prompted to log into the environment first. So how do your applications authenticate to AWS resources? As we know, this has to happen before being authorized to perform any actions. What credentials are used, and how is this authentication achieved? Identities, human or system, requiring this type of programmatic access to the AWS environment use access keys to authenticate. These access keys are comprised of two elements: access key ID and a secret access key ID. The access key ID is made up of 20 random uppercase alphanumeric characters, such as the one displayed on screen. The secret access key ID is made up of 40 random upper and lowercase alphanumeric and non-alphanumeric characters, as displayed. These access keys can be created for any IAM user who requires authentication from a programmatic perspective. When the keys are created, you are prompted to download and save the details, as the secret access key ID will only be displayed once, and if you lose it, then you'll have to delete the associated access key ID and recreate new keys for the user. It's worth noting that it's not possible to retrieve lost secret access key IDs, as AWS does not retain copies of these for security reasons in case they were compromised. These access keys must then be applied and associated with your system and application that we are using that requires the relevant access. For example, if you are using the AWS CLI to access AWS resources, you would first have to instruct the AWS CLI to use these access keys to authenticate and provide authorization. The method of performing this association varies based on the application and system that you are using. However, once this association has taken place, it ensures that all API requests made to AWS are signed with this digital signature. Before we move on, I want to give a quick demo on how we apply access keys to the AWS command line interface. So let's take a look. Okay, so let's look at how we apply access keys to the AWS CLI. If we go back to our CA user 1 that we used earlier for multi-factor authentication, we can look at their current permissions, which is defined as S3 read-only access. Now, to create some access keys for this user, we need to go across to security credentials and go down to access keys and create access key. So here we have the two parts, the access key ID and the secret access key. So now what we need to do, we need to add these details to the AWS CLI. So if I flip across to the terminal, and the command we type in is AWS configure. And here it asks for the access key ID. So let's go ahead and copy that. Paste that in. And now the AWS secret access key. Now it'll ask for a default region name. We'll just keep these as all the default settings. Same again with the output format. And there we go. So we've now configured our AWS CLI to use these new secret access key IDs. So now let's just clear the screen. Now we know this user had S3 read-only access. So let's test that out. So if we do AWS S3 LS, so that will list any buckets we have in S3, which should work because we know this user has read-only access. And there you go. You can see the buckets that are currently in S3. Now, if we wanted to make sure this was working correctly, we can try and create a bucket. Now, we know this user hasn't got access to do that. They only have read-only access. So this should fail. So AWS S3 MB to make bucket. And then we'll call the bucket Stu's image files. And there you go. It says access denied. So that shows the access keys have been applied to the AWS CLI correctly. As we discussed earlier when talking about passwords and how it's best practice to change a password after a set period of time, the same principle applies when it comes to access keys. By rotating your access keys, you are decreasing the likelihood of your environment and identities being compromised and gaining access to your environment. When rotating these keys, you should follow a simple 5-point process to ensure you don't lose access to your resources. Firstly, you should create a second access key. Now that includes both the access key ID and a secret access key ID for the same user. So now the user has two access keys associated to them. Instruct your application or system to start using the new access keys. Depending on what you are using will depend how you do this. For example, if you are using the AWS CLI, then you would issue the command AWS configure to add the new key information as we have just seen in the demonstration. At this point, you need to mark the existing access keys as inactive. Before deleting this now inactive access key, you should test your new access keys and verify that programmatic access is being allowed as expected. Finally, delete the old access keys from the associated user. As an authentication method from a programmatic perspective, access keys are a great solution. However, if you are applying access keys to applications running on EC2 instances to gain access to other AWS resources within your environment, then there is a more efficient and secure solution available. IAM roles provide an efficient and secure solution in authenticating and authorizing access, and their usage is considered a best practice. IAM roles are objects created within IAM and have a defined set of permissions associated to them, much like a normal user or group would have. However, they do not represent an identity like users. They are simply an object with a list of authorized permissions associated. When an EC2 instance is created, you have the opportunity to associate the EC2 instance with an IAM role. This option is only available during EC2 creation. If you have an existing EC2 instance that you want to have an IAM role assigned, then you must create an AMI image of that instance and recreate it from the new AMI, and then select the appropriate role. Once you have an EC2 instance with an associated IAM role, you can now install your application that will need to make API calls within AWS. By having a role associated to the EC2 instance, there is no need to apply access key IDs as we did previously. Instead, when your application attempts to access an AWS resource, dynamic temporary access keys will be supplied by the role to determine if access is authorized. Roles are not just for instances, they can also be assumed by a user, allowing them to switch from their current set of permissions to take the permissions given by the role. It's important to note that permissions from the user and the IAM role are not amalgamated. The permissions are swapped from the user to the IAM role. To switch to a role, permissions must first be given to the user, allowing them to switch to the role, authorizing them to use this new set of temporary permissions. Roles also take care of access key rotation as well, so there is no need to perform your own rotation of access keys, again as per our previous 5-step example. Recall that earlier I said it's more efficient to use roles for EC2 when requiring programmatic access over an IAM access key ID. This is because if you have multiple applications running on multiple EC2 instances, then when it comes to key rotation, you would have a number of applications to associate the new keys to. Okay, so moving on from IAM roles but sticking with EC2 instances, I want to talk about how we authenticate to newly created instances. And the process is slightly different for Linux and Windows operating systems, but the method is the same. The method uses AWS key pairs. You may think this is similar to what we discussed previously with the use of an access key ID and a secret access key ID, essentially a pair of keys. But key pairs are something completely different and provide an authentication method for a different purpose. When you create an EC2 instance, you are asked to select or create an EC2 key pair. So what is it and what does it do? A key pair, as the name implies, is made up of two components, a public key and a private key. These keys are 2048-bit SSH to RSA keys. The function of key pairs is to encrypt the login information for Linux and Windows EC2 instances, and then decrypt the same information, allowing you to authenticate onto the instance. The public key uses public key cryptography to encrypt data such as the username and password. For Windows instances, the private key is used to decrypt this data, allowing you to gain access to the login credentials, including the password. For Linux instances, the private key is used to SSH onto the instance. The public key is held and kept by AWS. The private key is your responsibility to keep and ensure that it is not lost. So going back to when you create your EC2 instance, you are given the opportunity to download the key pair in the form of a PEM file. Once you have done this, you must keep that file safe until you are ready to log into the associated EC2 instance. It's worth noting that you can use the same key pair on multiple instances. As I said previously, the process of how we authenticate to a Linux OS and Windows OS is slightly different, and the best way to demonstrate this is if I show you via demonstration. So let's take a look at how I use the PEM file containing the private key for each. Okay, in this demonstration I'm going to show you how to connect to a Linux box and a Windows box using your key pair or your PEM file that you would have downloaded on creation. As you can see, I've created two boxes here. One of them is a Linux box and another is a Windows. So let me show you how to connect to the Linux box first. So if you select it there and then click on connect, this screen will give you a couple of bits of information to allow you to connect to your Linux box over SSH. Firstly, you need to ensure that your key is not publicly viewable, and to do that you need to issue this command against your PEM file, which I've already done. and we have our public DNS name of the Linux box there. And then simply to connect, we run an SSH command, and it gives us the whole command here. So we run a SSH on our PEM file, and I've named it linux.pem for ease. And we'll connect with the username EC2user, which is the default user for Linux boxes, at the public DNS name. So let's go ahead and copy this command and see if we can connect. And there you go. We are up and running on the Amazon Linux AMI box here. So it's very simple and easy to connect to a Linux box. We simply use the PEM file within the connection string of an SSH command. So let's see how this differs to a Windows box. So if we go back to the management console, select Windows, connect, and here you can see you've got a couple of different options. We still have the public DNS name. Our username is administrator as opposed to EC2 user for Linux boxes. And then where we use the PEM file is to decrypt the password. So if we click on get password, then we need to select our key pair, so our PEM file. I've named it windows.pem for ease. We then click on decrypt password, and there you can see it's decrypted our password for the Windows box. So now what I'll do, I'll RDP onto the Windows box to make sure we can connect. So I'll copy our public DNS name, and I'm using Microsoft Remote Desktop. Let's create a new session, just call it Windows box. Connect via public DNS. We know our username is administrator. And then if we copy the password and then see if we can connect. Click on continue, negotiating credentials. And here we are, it's connected to our Windows box. So as you can see, the process was slightly different. For the Windows box, we use the PEM file to decrypt the password. And for a Linux box, we use the PEM file in the connection string to connect to it. Once you have authenticated to the EC2 instance the first time, you can then set up your own local authentication methods, such as local Windows accounts allowing other users to connect and authenticate to, or even use Microsoft Active Directory. AWS allows you to access and manage AWS resources, even if you don't have a user account within IAM, through the use of Identity Federation, which is the next authentication mechanism I want to discuss. Put simply, Identity Federation allows users from identity providers, IDPs, which are external to AWS to access AWS resources securely without having to supply AWS user credentials from a valid IAM user account. An example of an identity provider can be your own corporate Microsoft Active Directory. Federated access would then allow the users within it to access AWS. Other forms of identity providers can be any OpenID Connect web provider. Common examples of these are Facebook, Google, and Amazon. If you want to understand more about OpenID Connect, please see the following website. So what does this mean? Well, this means that if you need users to access AWS resources that already have identities that fit into these categories, then you could allow access to your environment using these existing accounts instead of setting each of them up a new identity within AWS IAM, effectively allowing for a single sign-on solution. As the vast majority of organizations today are using Microsoft Active Directory, this is an effective way of granting access to your AWS resources without going through the additional burden of creating IAM user accounts. As a part of the configuration process to implement federated authentication, a trust relationship between the identity provider and your AWS account must be established. AWS supports two types of identity providers: Web Identity Federation and SAML2 based federation. Web Identity Federation allows authentication between AWS resources and any public OpenID Connect provider, such as Facebook, Google, or Amazon. When it's set up and configured and an access request is made by a user to an AWS resource, perhaps an application, then their identity provider will exchange an authentication token for temporary authentication credentials. These credentials are associated to an IAM role with correct pre-configured permissions, allowing authorized access to the resource as defined by that role. For this example, the process could be managed more effectively with the use of Amazon Cognito, which helps manage user sign-in to mobile and web apps through federated access. For more information on Amazon Cognito, please visit this link. SAML2-based federations can allow your existing Active Directory users to authenticate to your AWS resources, allowing for a single sign-on approach. SAML stands for Security Assertion Markup Language and allows for the exchange of security data, including authentication and authorization tokens, to take place between an identity provider and a service provider. In this case, the identity provider is Microsoft Active Directory Service and the service provider is AWS. Once configured, let's take a look at how the Active Directory Authentication mechanism is established. This example will assume a user within an organization requires API access to S3, EC2 and RDS. This scenario will also include the use of an AWS service called Security Token Service, STS. The Security Token Service allows you to gain temporary security credentials for federated users via IAM, which are associated with existing IAM roles and policies. More information on STS can be found here. Let's run through this example. A user within an internal organization initiates a request to authenticate against the Active Directory Federated Service via a web browser using an SSO URL. If their authentication is successful by using their Active Directory credentials, SAML will then use a successful authentication assertion back to the user's client requesting federated access. The SAML assertion is then sent to the AWS Security Token Service to assume a role within IAM using the Assume Role with SAML API. STS then responds to the user requesting federated access with temporary security credentials with an assumed role and associated permissions, allowing S3, EC2 and RDS access in our example. The user then has federated access to the necessary AWS services as per the role permissions. This is a simple overview of how federation is instigated from the user for API access to specific AWS services. Corporate identity federation is always authenticated internally first by Active Directory before AWS. This brings us to the end of this lecture. Next, I will touch on how authorization is permitted across different AWS services. Hello and welcome to this lecture discussing how authorization can be granted within AWS. In an earlier lecture, I discussed the differences between authentication and authorization, and I just want to reiterate what they were, so I'll go over the definition of the two again. Authentication is the process of defining an identity and the verification of that identity. For example, a username and password. Authorization, that determines what an identity can access within a system once it's been authenticated. An example of this would be an identity's permissions to access specific AWS resources. As we have already seen, the main service that is responsible for managing and maintaining what an AWS identity is authorized to access is governed by IAM, Identity and Access Management. So let's start with IAM and how these permissions are implemented and associated with different identities, allowing their authorization to use specific services and carry out certain functions. When an identity is authenticated to AWS, the way in which permissions are given to that identity varies depending on that identity's own user permissions and its association with other IAM groups and roles. Let's take a quick recap at users, groups and roles. IAM users are account objects that allow an individual user to access your AWS environment with a set of credentials. You can issue user accounts to anyone who needs to view or administer objects and resources within your AWS environment. Permissions can be applied individually to a user, but the best practice for permission assignments is to add the user to an IAM group. IAM groups are objects that have permissions assigned to them via policies, allowing the members of the group access to specific resources. Having users assigned to these groups allows for a uniform approach to access management and control. IAM roles are objects created within IAM, which have policy permissions associated to them. However, instead of just being associated with users as groups are, roles can be assigned to instances at the time of launch. This allows the instance to adopt the permissions given by the role without the need to have access keys stored locally on the instance. Permissions are granted to users, groups, and roles by means of an AWS IAM policy. This policy is in the form of a JSON script. There are a number of pre-written AWS policies which are classed as AWS managed policies. You can also create your own custom managed policies too. The AWS managed policies cover a huge range of AWS services at different authorization levels, from read-only to full access. And at the time of this course production, there are currently 218 AWS managed policies in place. If your security requirements fit with one of these AWS managed policies, then that's great and you can start using it right away by associating users, groups, or roles to it. However, it's more than likely that these AWS managed policies are not a perfect match for permissions you want to assign to an authenticated user. In this instance, you can copy and tweak the policy and make it fit for your requirements exactly. When it comes to security, you can't be lazy, as this leads to mistakes and vulnerabilities. You can't afford to take shortcuts and you need to define your permissions, ensuring they only allow authorized access to services and features that are required. IAM policies are made up of statements following a set syntax for allowing or denying permissions to an object within AWS. Each policy will have at least one statement with a structure that resembles the following. Statement. This defines the main element of the policy and groups together the permissions defined within it via the following attributes. Effect. This will either be set to allow or deny. These are explicit. By default, access to your resources are denied, and so therefore if this is set to allow, it replaces the default deny. Similarly, if this was configured as deny, it would override any previous allow. Action. This corresponds to API calls to AWS services that authenticate through IAM. This example represents an API call to delete a bucket, the action within S3. You are able to list multiple actions if required by using a comma to separate them. Wildcards are also allowed. So for example, you could create an action to carry out all APIs relating to S3. Resources. This specifies the actual resource you wish the permission to be applied to. AWS uses unique identifiers known as ARNs, Amazon Resource Names, to specify resources. Typically, ARNs follow the following syntax. Let's break this down and take a look at each of these segments. Partition. This relates to the partition that the resources is found in. For standard AWS regions, this section would be AWS. Service. This reflects the specific AWS service, for example S3 or EC2. Region. This is the region where the resource is located. Now remember, some services do not need a region specified, so this can sometimes be left blank in those circumstances. Account ID. This is your AWS account ID without hyphens. Again, there are some services that do not need this information, and so it can be left blank. Resource. The value of this field will depend on the AWS service you are using. For example, if I were using the action S3 delete bucket, then I could use the bucket name that I wanted the permission to delete. And in this example, Cloud Academy is the name of the bucket. Condition. This element of the IAM policy is an optional element that allows you to specify when the permissions will be activated based upon set conditions. Conditions use key value pairs, and all conditions must be met for the permissions to be activated. For example, there may be a condition only permitting requests from a specific source IP address. A full listing of these conditions can be found here. Now we have a basic understanding of how JSON scripts are put together and their general flow. Let's see how we can modify existing policies to tweak them to your needs. To copy and edit an existing AWS managed policy is a very simple and easy thing to do, and can save you a lot of time trying to recreate your own if you just need a few small tweaks. So I'm currently within the AWS Management Console at the dashboard of IAM. So from here, you just need to go down to Policies, and then up to Create Policy. Now you can see you've got three options here: copy an AWS managed policy, the policy generator, or create your own. For this demonstration, we want to copy an existing AWS managed policy, and then we can customize it to fit our needs. So we can select that. Now you can filter from this policy list to save you scrolling through the tens or hundreds that there are. So what I would be inclined to do is to search for roughly what you're looking for. Let's have a look at S3. Let's take a look at the S3 read-only access. So we'll select that. And now you can see what the policy looks like. So this is the JSON document, and you can see that it allows the S3 get and S3 list actions, which will essentially give you read-only access to S3 to any resource. So let's modify this to include an additional permission, for example, create bucket. So we can directly edit this policy document and add in our own. So S3 create bucket. So now we have read-only access, and also we are allowed to create buckets as well. If we click on validate policy, and that will just confirm that the entries we've made are okay. And you'll see along the top here, it says this policy is valid. If you did edit it and it wasn't quite correct, then it would let you know. So for example, if I removed this comma here and tried validate policy again, it will let us know that this policy contains the following JSON error on the specified line. It tells you what it expected instead of what it actually has. So if we go back to line 8, add back in our comma and say validate, and you can say this policy is valid. And then from here, all we need to do is give this a new policy name. We can call it S3 custom policy. And then all we need to do is click on create policy. And that's it. Now we can verify that that policy exists. We can click on the filter here and say customer managed. Because we've edited the AWS managed policy, it now becomes a customer managed policy. So, and we can see down here, here's our policy, S3 custom policy. If we can click on it, we can see the JSON document. And that's it. If you don't feel confident enough to edit existing AWS managed policies, then you could use a tool provided within IAM called the IAM Policy Generator. This allows you to create an IAM policy using a series of drop-down boxes without the need of editing a JSON document itself. The following demo will quickly show you how to access this policy generator and create an example policy. Okay, so to create a policy using the AWS policy generator is again very simple like we've done previously. I'm starting on the screen within IAM and I'm under policies at the moment. So from here, all you need to do is click on create policy. And again, we have the three options, but this time we want to use the policy generator. So click on select. Now we've got a number of drop-down boxes and options here. So we've got an effect, which we can either have as allow or deny. For this example, we'll have allow. We'll then have a list of AWS services. As you can see, there's quite a lot in the list. And we'll select Amazon S3. And now we can pick all the actions associated with S3. If we tick this one here, all actions, then we get everything. Or we can just pick specific permissions. Let's go for create and delete buckets. And then we have to supply the Amazon resource name. So for S3, that'll be on AWS S3, and then all resources, add statement. And you can see here at the bottom, we have an allow effect for the S3 create and delete buckets to all resources within S3. And then we click on next step. And we can see here that it's created the JSON policy document for us. So based on those drop-down selections, we now have a full policy document that we can use. And then we can click on validate policy. And as before, you can now see that this policy is valid. So there's no errors in this policy. And now we can give this policy a name. Let's call it S3 create and delete. And then click on create policy. And again, we can have a look and verify that our policy is there by filtering on customer managed. And here we have our S3 create delete policy. And there you go. That's how you create a policy using the policy generator. So far, we have covered how to create IAM policies from both an AWS managed perspective and via the policy generator. However, if you are completely at ease writing your own JSON scripts and want to define your own tight and well-written IAM policies, then you have this option available to you as well. All you need to do is to give your policy a name and a description, and then start writing your permission statements, authorizing any associated identities to access or restrict access to AWS resources. Once you get used to the syntax and benefits of writing your own policies, you will be able to effectively and efficiently lock down access to your resources to ensure they are only accessed by authorized API calls. There are many commands that can be applied and controlled through an IAM policy, but they're a bit beyond the scope of this course. However, AWS does provide great API listings for the different services through their extensive documentation for advanced policy writers. Let's now take a step away from IAM and move our attention to S3, Simple Storage Service. This is one of AWS's most common storage services and is used by a multitude of other AWS services, so it's worth devoting some time to see how S3 handles its own authorization. There are multiple ways an identity can be authorized to access an object within S3, which overlap with the IAM mechanisms we have already discussed. So how does a user or service get the correct level of authorization? First, let's define the different methods that permissions can be applied within S3. S3 bucket policies and S3 ACLs, access control lists. Bucket policies are similar to IAM policies in that they allow access to resources via a JSON script. However, as the name implies, these bucket policies are only applied to buckets within S3, whereas IAM policies can be assigned to users, groups or roles as we previously discussed. In addition, IAM policies can also govern access to any AWS service, not just S3. When a bucket policy is applied, the permissions assigned apply to all objects within that bucket. This policy introduces a new attribute called principals. These principals can be IAM users, federated users, another AWS account, or even other AWS services, and it defines which principals should be allowed or denied access to various S3 resources. Principals are not used within IAM policies, as the principal element is defined by who is associated to that policy via the user group or role association. As bucket policies are assigned to buckets, we need to have this additional parameter of principals within the policy. As you can see from this example, a bucket policy is very similar in terms of layout and syntax to that of an IAM policy. However, we do have the principal attribute added. This value must be the AWS ARN of the principal, and in this example we can see Cloud Academy, as a user within IAM, is allowed to delete objects and put objects within the Cloud Academy bucket identified under the resource parameter. S3 bucket policies also allow you to set conditions within the policy, allowing a fine-grained permission set to be defined. For example, you could allow or deny specific IP subnets to access the bucket, or perhaps even restrict a specific IP address. This is another level of access control taking place at the network level that helps to tighten access, ensuring only authorized access is permitted. I now want to move on to S3 ACLs to show you how these differ. This access mechanism predates IAM and so is quite an old access control system. S3 ACLs allow identities to access specific objects within buckets, a different layered approach than bucket policies, which are applied at the bucket level only. ACLs allow you to set certain permissions on each individual object within a specific bucket. These ACLs do not follow the same format as the policies defined by IAM and bucket policies. Instead, they are far less granular and different permissions can be applied depending if you are applying an ACL at the bucket or object level. The grantee is the resource owner and is likely to have full control over that object and on new bucket creations. This is typically the AWS account owner. The grantees are defined by the following categories. Everyone. This will allow access to this object by anyone, and that doesn't just mean any AWS user, but anyone with access to the internet if the object is public. Any authenticated AWS users. This option will only allow IAM users or other AWS accounts to access the object via a signed request of authentication. Log delivery. This allows logs to be written to the bucket when it is being used to store server access logs. Me. This relates to your current IAM AWS user account. From within S3 via the AWS Management Console, these permissions can be applied through a series of checkboxes, and if all options are selected, then that grantee is considered to be authorized to have full control of the object. You can have up to 500 grantees on any object. We have spoken about a number of ways an identity or principal can be authorized access to a resource or object within AWS. But what happens if a principal who belongs to a group and accesses an object in a bucket with S3 ACLs, bucket permissions, and their own IAM permissions? Within all of this authorization applied to the principal, how is this access governed if there are conflicting permissions to the object in the bucket that they are trying to access? Well, AWS handles this permission conflict in accordance of the basis of least privileged. Essentially, by default, AWS dictates that access is denied to an object, even without an explicit deny within any policy. To gain access, there has to be an allow within a policy that the principal is associated to or defined by within a bucket policy or ACL. If there are no denies defined, but there is an allow within a policy, then access will be authorized. However, if there is a single deny associated with a principal to a specific object, then even if an allow does exist, this explicit deny will always take precedence, overruling the allow, and access will not be authorized. I'd now like to just give a quick demo of how to create S3 ACLs and S3 bucket policies. Okay, for this demo, I'm going to show you how to look at the S3 ACLs and edit those, and also how to create an S3 bucket policy. So I've created a bucket here from within S3 called CA Demo Bucket. And looking at the properties of this bucket, if we go down to permissions, here you'll see the permissions related to the ACL, the access control list. The grantee is the account owner. So if we wanted to add more permissions to this ACL, we can click on Add More Permissions. Select another grantee. I'll just select me. And then we can just use the tick boxes to select the permissions that we want. So list and upload and delete. And then click on Save. And that will now give my user list and upload and delete permissions to this bucket. And for S3 ACLs, it's as simple as that, really. So moving on to bucket policies, let's just delete this. So let's add a bucket policy. Now you can either write your own policy here if you're confident enough, or you can select a sample bucket policy or use the AWS policy generator. So let's go ahead and use the generator. Type of policy will be an S3 bucket policy. The effect we'll have is allow. So the principal is going to be an AWS user in this demonstration. So if we go ahead and look at our user, the one we created earlier was CA user 1. Here's the ARN of this user, so we shall copy that. And if you notice, the permissions that this user's got is only read-only access to S3. It's one of the AWS managed policies that's assigned to that user. So we'll put in the ARN of the principal. Service is S3, and the action we will have will be put object. And the ARN of the bucket will be ARN, AWS, S3, CA demo bucket, and then any resource. Let's add conditions as well for this. So on the condition of an IP address with the source IP being mine, which is 90.198.222.3. So we'll add that condition. We'll add the statement. So here we can see that the principal is the CA user 1 is allowed to put objects within the CA demo bucket on the condition that the source IP address is 90.198.222.3, which is my IP address. Click on Generate Policy. We can then copy that and paste it into our bucket policy editor. Click on Save. And that's it. That's the bucket policy applied. So what I'm going to do now is log out of this account and log in with the CA user 1 account and try and put an object in that bucket. Okay, so I've logged back in as CA user 1. So I want to try and test that bucket policy now by putting an object within this bucket. So as you can see, I'm within the CA demo bucket. So if I go to upload, add files, pick a random file and say start upload. And there you can see the object has been uploaded. So with the use of a bucket policy, we was able to grant additional permissions to this user to allow them to add objects to this bucket, with the inclusion of the conditions as well using the source IP address. Permissions and authorization can exist at multiple layers within the AWS framework. We have looked at specific user and principal permissions and how the authorization process is managed. When we discussed S3 bucket policies, we briefly touched on conditions and how this could be configured to allow or deny access based on IP addresses, for example. This network level access control can also be used within your virtual private cloud, VPC, to authorize network traffic in and out of a particular subnet. It's managed differently and offers greater control through the use of network access control lists, or NACLs. In the beginning of this course, we listed AWS NACLs as an access control mechanism, and indeed they are. However, they provide permissions at a network layer. NACLs provide a rule-based security feature for permitting ingress and egress network traffic at the protocol and subnet level. In other words, ACLs monitor and filter traffic moving in and out of your subnets, either allowing or denying access dependent on rule permissions. These NACLs are attached to one or more subnets within your virtual private cloud. If you haven't created a custom NACL, then your subnets will automatically be associated with your VPC's default ACL, and in this instance, the default allows all traffic to flow in and out of the network as opposed to deny. The rule set itself is very simple and has both an inbound and outbound list of rules, and these rules are comprised of just 6 different fields. These being rule number. ACL rules are read in ascending order, and as soon as a network packet is received, it reads each rule in ascending order until a match is found. For this reason, you will want to carefully sequence your rules with an organised numbering system. I would suggest that you leave a gap of at least 50 between each of your rules to allow you to easily add new rules in sequence later if it becomes necessary. Type. This drop-down list allows you to select from a list of common protocol types, including SSH, RDP, HTTP and POP3. You can alternatively specify custom protocols, such as varieties of ICMP. Protocol. Based on your choice for type, the protocol option might be greyed out. For custom rules like TCP and UDP, however, you should provide a value. Port range. If you do create a custom rule, you'll need to specify the port range for the protocol to use. Source. This can be a network subnet range, a specific IP address, or even left open to traffic from anywhere. Allow and deny. Each rule must include an action specifying whether defined traffic will be permitted to enter or leave the associated subnet or not. So looking at these rules, authorization is permitted or denied by the associated subnet, depending on the verification of the parameters identified in points 2 to 5. This data is analysed from within the network packet itself, so we are not authorising a principal here like we have been looking at with IAM and S3. Instead, we are authorising the network packet itself. It's important to note that NACLs are stateless. Therefore, when creating your rules, you will need to apply an outbound reply rule to permit responses to inbound requests. I have seen NACLs used very effectively to prevent DDoS, distributed denial of service attacks. If traffic somehow manages to get past AWS's own DDoS protection undetected and you are being attacked from a single IP address, you can create a NACL rule that will deny all traffic from that source right at the subnet level, and the traffic will not be authorized to go any further. Just a small point, and this applies to all the authentication and authorization mechanisms I've mentioned thus far. Your NACLs will require updating from time to time, and you should regularly review them to ensure they are still optimized for your environment. Security is an ongoing effort and needs regular attention to ensure its effectiveness. Having the ability to authorize or deny network packets at a network level is great, but can the same be accomplished at an instance level? The answer is yes. Let's see how this level of authorization works. AWS security groups are associated with instances and provide security at the protocol and port access level, much like NACLs, and as a result they also work much the same way, containing a set of rules that filter traffic coming into and out of an EC2 instance. However, unlike NACLs, with security groups there isn't a deny action for a rule. Instead, if there isn't a rule that explicitly permits a particular packet, it will simply be dropped. Again, the rule set is made up of two rule sets, inbound and outbound. But security groups are stateful, meaning you do not need the same rules for both inbound and outbound traffic, unlike NACLs which are stateless. Therefore, any rule that allows traffic into an EC2 instance will allow any response to be returned without an explicit rule in the outbound rule set. Each rule is comprised of 4 fields: type, protocol, port range, and source. Let's take a look. Type. The drop-down list allows you to select common protocols like SSH, RDP, HTTP. You can also choose custom protocols. Protocol. This is typically grayed out, as it's covered by most type choices. However, if you create a custom rule, you can specify your protocol here. Port range. This value will also usually be pre-filled, reflecting the default port range or port range for your chosen protocol. However, there might be times when you prefer to use custom ports. Source. This can be a network subnet range, a specific IP address, or another AWS security group. You can also leave access open to the entire internet using the anywhere value. We can clearly see here that authorization to the instance can only be permitted if the packet meets conditions within the 4 parameters. Again, we are not authorizing a principal here, it's the network packet itself. Security groups are a great way to authorize the use of particular ports for communication, whilst restricting all other communication over denied ports. For example, you could have a number of SQL RDS instances that you want to write to from a group of EC2 instances. In this case, you could create a security group for the SQL RDS instances and another for the EC2 instances. You would then authorize communication to happen over specified permitted ports, such as 1433 and 1434 used by SQL, between the two groups. All other communication will be dropped and denied, which in turn enhances security on your AWS infrastructure. That brings us to the end of this lecture on authorization within AWS. Coming up next, we'll look at how we can track and audit identities that have been authenticated and are authorized to access specific resources. Hello and welcome to this lecture on AWS Accounting. Firstly, I want to clarify what this topic covers and what I mean by accounting. By accounting, I refer to tracking what actions a user performs during their session while authenticated to the AWS environment. This information can then be used to determine the costs incurred by that identity. This can include information such as resources used, the amount of data transferred in and out of AWS, and any other actions with cost implications. This information can all be used to assist with billing, planning, and ensuring resource capacity and utilization is optimized. Let's start by understanding the billing process and how this is calculated for an AWS account. When it comes to monitoring and managing your AWS financial information, you will want to ensure this privilege is restricted to those only authorized to do so. By default, your AWS account owner has full access to all billing information. No other users initially have access. The first time that your root account tries to access the billing information, you will need to perform 3 steps, as it's not automatically activated and isn't initially visible. Firstly, log into the AWS Management Console as the AWS account owner, or root. Select your account name in the top right and select My Account. Select Edit next to IAM user access to billing information and select the checkbox to activate. The root account can now access the billing and cost management from within the console by selecting your username and account in the top right corner and selecting Billing and Cost Management. From here, you are able to access information such as your bills, budgets, reports, payment history, and method of payment, etc. Clearly, this is very sensitive information. If you require other users to access billing information, you have to grant specific permissions via an IAM policy. Let's take a high-level overview at some of the most common topics within billing and cost management. These being bills, cost explorer, budgets, reports, cost allocation tags, and consolidated billing. If we look at the bills section, we will see precisely what we'd expect: AWS bills for the account. From here, we can see our current monthly expenditure for AWS using the exchange rate valid at the time to your local currency. We also have the ability to drill down into where these costs have been incurred from a service level. We can also navigate back in history to see your previous month's bills if you need to see them. If we wanted to interact with this billing data, then we can download the entire bill as a CSV file to allow us to do so, for example from within Microsoft Excel. Moving on to Cost Explorer, this is a useful and powerful tool within billing and cost management. It allows you to view historical billing information in a graphical format, giving you greater insight to your AWS spend. A valuable tool that can help to identify where you should be focusing your cost optimization efforts. It also has the ability to forecast your estimated spend up to 2 months ahead using existing data as a reference. If you can see that your estimated future bills are becoming too high, you will have the time to identify where you can make and initiate cost reduction mechanisms to help mitigate the risk. Cost Explorer comes configured with 3 predefined views, which are commonly used to analyze spending across your account. Monthly Spend by Service view. This covers the current and previous 2 months and is grouped by AWS services. Monthly Spend by Linked Accounts view. This covers the current and previous 2 months as is grouped by linked accounts. Daily Spend view. This covers the daily spend over the previous 60 days. When viewing these graphs and charts, you can easily notice unexpected peaks of service usage that are out of trend, which could highlight possible misuse of services within your account. This could be caused by a whole host of security concerns, such as incorrect permissions set on users or other identities that have more authorization than they should have, creating large EC2 instances, for example. Billing and cost management budgets are again self-explanatory. Budgets can be created to help you manage costs and usage across your environment. You can configure budgets to alert you via the use of SNS, Simple Notification Service, when certain thresholds are met, allowing you to take effective action. Data for calculating budgets is taken from Cost Explorer, so when used together, you can create an effective solution for managing your expenditure. One point to make with AWS budgets is that you can set up a new budget that isn't specifically cost related. For example, you could set up a budget to measure usage within your services, such as how many gigabytes are used within a particular S3 bucket, or even how often a particular API is being called. This could potentially be used to aid with security. If there is a high restriction on a specific API function being called, then a low threshold could be set on the budget to monitor the number of calls, and once this threshold is met, an SNS message could be sent to the security team to identify where and why this API is being called. Similarly to budgets, reports allow you to report on cost and usage. Reports can be custom generated and can produce extremely detailed information on your service's costs and usage. These reports are then stored within an S3 bucket for you to review. You must ensure you set the correct level of permissions on this S3 bucket, ensuring only those requiring access can access it. Discussed previously in this course, this can be achieved by IAM policies, S3 bucket policies, or S3 ACLs. These detailed reports can be uploaded to either AWS Redshift or AWS QuickSight for further analysis by business intelligence applications to gain further insights into your usage and cost patterns. A simple but very effective way of combining services that share a common characteristic, such as a project name or a departmental function, can be grouped together by the use of tags. When you create EC2 instances, for example, you can associate a custom tag name such as sales or engineering. These tags can then be selected under cost allocation tagging in billing and cost management to filter all costs associated to the AWS resources that share this tag name. Reports can be generated based off of those tags to accurately define costs associated to any of your custom configured tags within your environment. Lastly, within this section on billing and cost management, I want to talk about consolidated billing between linked AWS accounts. If you had multiple AWS accounts, possibly for different functions, customers, or even environments, then you can link them together to allow you to securely consolidate all your AWS billing via a single master paying account. It's important to point out that by linking accounts, only the billing information is linked. No other information can be accessed between the accounts. Each account still acts completely independent of the other. By consolidating the billing into one paying account, simplifies your AWS finances. It provides a simple overview of all your accounts each month. Only the paying account is charged, and from here you can see the usage of all other accounts in one place, through other features we have already discussed, such as Cost Explorer. If you link your account for consolidated billing, I strongly suggest that you enforce strong security on the paying account and implement multi-factor authentication. So as we have highlighted, you are able to extract a lot of information from your AWS bill using the different features and tools. These tools and features offer you the ability to highlight and be alerted of potential security breaches, such as unauthorized EC2 launches. If you find such an anomaly that is costing your account more than expected, how can you find out who or what is responsible? One way is to take a look at AWS CloudTrail. AWS CloudTrail tracks and monitors AWS API calls made within your environment, regardless of the method used. It can be initiated from other AWS services, a user from within the AWS Management Console, AWS CLI, or from an SDK. If an API call is made to create, modify, or delete an AWS resource, then AWS CloudTrail will log the request in an event, along with key data associated with the request. When an authenticated user is accessing resources on AWS, there are a lot of API calls being made. Most of these will be authorized and legitimate. However, some of them may be trying to penetrate your network and gain access to unauthorized data. A tool like CloudTrail is very effective in identifying valid and malicious API calls. The details recorded within CloudTrail events contain the following information about the API call: the identity of the caller, the timestamp of when the request was initiated, the source IP address, the request parameters, the response elements returned by the AWS service. Having these details is great from a security point of view, as it provides very specific information about where an API call originated and which identity initiated the request. If malicious activity was found, then a number of security blocks could be implemented quickly to prevent the user from causing any more damage. For example, their account could be removed and their IP address blocked at a NACL level. Looking at your API call history within CloudTrail, you may need to find a particular event quickly, perhaps in a circumstance where you are trying to mitigate a security breach. To help you with this, you can enable a number of filters which will help you locate and identify the data you need. These filters are time range, event name, username, resource name, and resource type. Between the use of events recorded and the filtering possibilities, it's possible to track exactly what actions a user carried out during their session, how long that session lasted, and if they were successful or unsuccessful. This makes the CloudTrail service a great security analysis tool. When events are created by CloudTrail, they are compiled into logs which are then delivered and stored in an S3 bucket, much like billing and cost management reports are. Again, be sure to apply the correct security level to this S3 bucket. By default, these log files are stored in S3 with server-side encryption, SSE, for additional security. The encryption is managed by the S3 service itself, and so when the log file is stored, S3 automatically encrypts it using its own keys, and when the log file is read by someone with authorization, S3 will use its own decryption keys to open the file. Your CloudTrail logs can hold very sensitive information, and as a result, this default SSE encryption is valuable. However, to tighten security even further, you can use SSE with KMS, which is the AWS Key Management Service, allowing you to use your own keys to encrypt the log files. CloudTrail isn't only integrated with S3, it also has a close relationship with AWS CloudWatch too. AWS CloudWatch is a monitoring service that allows you to view and track specific metrics from other AWS services. CloudWatch also allows you to create alarms if custom monitoring metric thresholds are reached, allowing your operations team to investigate potential issues. Logs from CloudTrail can be sent to CloudWatch to allow metrics and thresholds to be configured, which in turn can utilize SNS to create notifications of specific events relating to API activity. CloudWatch allows for any event created by CloudTrail to be monitored. This enables a whole host of security monitoring checks to be created. A great example of this is to be notified when certain API calls requesting significant changes to be made to your security groups or NACLs within your VPC. Other examples of these checks that are common within organizations are API calls relating to starting, stopping, rebooting, and terminating EC2 instances. If instances are being created that shouldn't be, your AWS costs could rise dramatically and quickly. Also, if instances are being rebooted or stopped, this could have a severe impact to your services if they are not configured in a high availability and resilient solution. Changes to security policies within IAM and S3. If changes are being made to your policies that shouldn't be, access can be inadvertently removed for authorized users and access given to unauthorized users, having a massive impact on operational services. Even a minor change to a policy can pave the way for an untrusted user to exploit the error. Failed login attempts to the management console. Monitoring failed attempts here can help to prevent unauthorized access at your environment's front door. API calls that result in failed authorization. Not only does CloudTrail track successful API calls, whereby the correct authorization was met by the authenticated identity, but it also tracks unsuccessful API requests too, which would likely be due to permissions applied. Special attention should be applied to these unsuccessful attempts, as this could be a malicious user trying to gain access. However, it could also be a legitimate user trying to access a resource they should have access to for their role, but the incorrect permissions have been applied within their associated IAM policy. When used effectively, you can clearly see that AWS CloudTrail can be a strong tool for tracking, identifying, and monitoring a user's actions within your AWS environment. That brings us to the end of this lecture. Coming up next, we'll just have a quick summary on the course. Hello and welcome to this short lecture to complete and summarise this course. Authentication, authorization, and accounting is key within any infrastructure, from different AWS environments such as test, dev, and production, to different departments using your AWS infrastructure such as sales and marketing, etc. If you overlook security from an identity and authorization perspective, you could leave yourself open to security loopholes, which in turn can lead to abuse from not only internal users, but external as well. Security remains the highest sticking point within cloud computing. It's the one key topic that consistently gains attention and requires constant and considerable effort to get right and implement efficiently. In order to do this correctly, a clear understanding and definition of security terms are essential, such as the clear differences between authentication, authorization, and access control we spoke about in one of the early lectures of this course. If you want to be an effective security expert, you need to know the differences between these terms to allow you to select and architect the right solution to meet your needs. There are so many different methods of authentication and granting permissions, it can get a little overwhelming when selecting the most effective mechanism. However, when doing so, implement the solution that meets the security level of the data and resources that you are protecting. If the data or resource is highly sensitive, then you would want to implement multiple levels of authentication, such as MFA, in addition to multiple levels of authorization at different levels. The more restrictions that are in place, the harder it is to breach. With potentially hundreds or thousands of users accessing your AWS environment, to create, modify, or delete resources, tracking this access can be crucial in resolving operational issues and security breaches and threats. This is where AWS CloudTrail, by tracking every API call, plays a great role in helping to account for actions made by an identity. This information can be used to track costs incurred by particular users should they have launched a number of instances with a single API call. Billing also plays a part in helping to secure your infrastructure. Analysis of your billing information allows you to track and notice trends occurring in your infrastructure. Any anomaly outside of these predicted trends could be a security breach that needs investigation. Implementing numerous authentication methods at the correct levels, along with multiple authorization mechanisms where identities can be tracked and monitored throughout their authenticated session, in addition to graphical billing analysis, allows you to create an effective, secure, and proactive security analysis solution. I would recommend you take a look at our labs we have here at Cloud Academy, as there are a number of AWS labs covering security, such as advanced IAM and S3 policies, and the creation of VPC subnets using NACLs. So feel free to take a look at these in your own time to become more familiar on how to set these up within a real environment. If you have any feedback on this course, positive or negative, please do leave a comment on the landing page of this course. Your feedback is greatly appreciated. That brings us to the end of this lecture and the end of the course. I hope you have found it useful and has answered some questions you may have had. Thank you for your time and good luck with your continued learning of cloud computing. Thank you.